All right, so let's tackle this second example from the using the general properties of reaction enthalpy topic. Here, we're giving our thermochemical equation, and the problem states that a chemist measures the enthalpy change, delta H, during the following reaction. Here I've got C6H6 benzene reacting with molecular hydrogen gas to produce ethylene, which has a chemical formula of C2H4. Now, when I look at the enthalpy change for this reaction as written, it tells me that when 1 mole of benzene, liquid benzene, reacts with 3 moles of hydrogen gas to produce 3 moles of ethylene, or C2H4, that it requires 108 kilojoules of heat. And I see that delta H is positive, which tells me that this is an endothermic process, which means heat is absorbed from the surroundings into the system. And so if this reaction were happening in a vessel or a flask and I were to touch the flask after the reaction has proceeded, it would feel cold to me, to my hands. Now, using this information, let's complete the table below. So, this first reaction here, we've got 1/3 of a mole of benzene reacting with 1 mole of hydrogen to produce 1 mole of ethylene. Now, as I look at it, I know that number one, this is not the reverse of this original process. And so I do not need to change the sign of the enthalpy change. But I do see that the amounts of the substances, the reactants and products involved in this particular reaction are different. How are they different? Well, I've divided all of the original molar amounts by 3. So the original mole amount here was 1 mole, 3 moles, and 3 moles. Dividing by 3, I ended up with 1/3. 3 divided by 3 is 1, and 3 divided by 3 is 1. And so to find the enthalpy change for this reaction as written, well, I need to take the enthalpy change for this reaction, which was 108 kilojoules per mole of this reaction, and divide it by 3. And so what I would get in my calculator if I do that is 36.0 kilojoules. Now they ask me here to round each of my answers to the nearest kilojoules per mole, and so I would just round that to 36 kilojoules. And just to very briefly explain what they mean here when they say to the nearest kilojoules per mole is they mean per mole of the reaction as written. And so this will be 1 mole of this reaction as it is written following the stoichiometric coefficients given of 1/3 of a mole of this, 1 mole of this, and 1 mole of this. Now let's look at the second reaction here. I've got gaseous ethylene, C2H4, decomposing into benzene and molecular hydrogen gas. And so right off the bat, I see that, well, this process is reversed. And so that means the sign of delta H must be the opposite of what it is up here. Up here, this is an endothermic process. Delta H is positive, and so the sign of delta H must change to be negative now. Okay? Also, I see that all of the mole amounts of the substances involved in this reaction have been halved. How do I know they've been halved? Well, I had 1 mole of this, 3 moles of this, and 3 moles of this. Now I have 3/2 moles of ethylene. I've got 1/2 mole of benzene, and I've got 3/2 moles of hydrogen gas, molecular hydrogen. So I essentially took all of these stoichiometric coefficients and divided them by 2. So because I have the amount of matter in this reaction, well, I take the enthalpy change for the original reaction, which is now exothermic, so it'll be negative 108 kilojoules, and I divide it by 2, or I have it. And so what I get for my enthalpy change of the second reaction is negative 54 kilojoules, rounded again to the nearest kilojoules per mole. And then look at this final reaction from this problem. I've got 3 moles of ethylene, 1 mole of benzene, 3 moles of hydrogen gas. When I look at the original reaction here, I started out with 1 mole of benzene as a reactant. Here I have 1 mole of benzene as a product. That tells me again that this reaction is reversed from the one given in the original information. Okay? And so because I have reversed the reaction, well, I'm going to also reverse the sign of the enthalpy change. Okay, so the enthalpy change will not be 108 kilojoules, but now it'll be negative 108 kilojoules, which means that this is an exothermic process as written. Did I change the amount of matter of the substances involved in this reaction? No, I did not. I still have 3 moles of this, I still have 1 mole of this, and I still have 3 moles of this. So the only thing that changed was the sign here of the enthalpy change. It still involves 108 kilojoules of heat, but now it is not 108 kilojoules of heat needing to go into the system, but it is 108 kilojoules of heat given off by the system into the surroundings. So just to be clear and to reiterate, our final answer would be negative 108 kilojoules.